Hello everyone, I'm Emergent. I'm a doctoral researcher in the University of Luxembourg, and this is the second video of a video series about large language models. I made a soft introduction in the previous video. Now I will explain the three important aspects of LLM, large language models, by using this mind map. Mind maps are always helpful for me, especially to understand the big picture of the topic. I hope it will be helpful for you too. And main source of this video is the latest comprehensive survey paper about large language models. A survey of large language models. Let's start. First of all, large language models are transformer language models because they are all using transformer architecture. And PLMs, pre-trained language models such as BERT or GPT, are also transformer-based models, but the biggest differences are model size and training data. LLMs are much more bigger than PLMs, and they are trained on massive text data. And some of the popular LLMs are GPT-3, 4, Palm, Galactica, Llama. Actually, we have more. We don't have only GPT as LLMs, and I will show others. And another important point is primarily LLMs are designed to understand and generate natural language and solve complex tasks. And you will see that some of the advanced LLMs, are able to process image, not only text. Now let's elaborate large language models theory and why are they so powerful. Before using, what should you know about LLMs? I will try to answer these questions with three important aspects. Firstly, scaling laws. I mentioned that LLMs and PLMs have similar objectives and architecture, the transformer architecture. However, performances and abilities are not similar. The first reason, LLMs are significantly bigger in terms of model size, data size, and total compute. Then the question, should we increase the model and data size as much as possible to increase the performance of LLMs? In other words, are bigger models always better? Not exactly, we have different approaches about scaling laws. So let's look at them. The first one is called as Cave scaling law by the authors of this survey paper, and it suggests allocating more computational resources on model size than data size. Another approach is very popular today, chinchilla scaling law, and it suggests that both model size and data size should be increased in equal proportions. Of course, this model size and data size, they are not only parameters. Training data size, domain, the quality of the data, the architecture, and the advanced techniques are other parameters. They are also important and they affect the performance. And here also we have another important point. According to experimental studies, it is shown that some abilities are unpredictable according to the scaling law, and they can be observed only when the model size exceeds a certain level. We don't have a standard threshold value for all models, but this behavior was observed for different models. I will show, but firstly, let's look at those abilities. And the second aspect, emergent abilities. The definition is simple. Abilities that are not present in small models but arise in large language models. Those are emergent abilities. And the idea is that performance of the model rises significantly when the scale reaches a certain level. Let's look at this figure, then it will be more clear. So as you see here, we have different models, Lambda, GPT-3, Chinchilla, Palm, and also different tasks, arithmetic, transliterate, word unscramble, truthful question answering, grounded mappings. And if you zoom in the figures, you will see that after a certain level, for example here, for this level, here, okay, here, as you see, after a certain level, the performance of the models increased dramatically. For this task, we have GPT-3 and Lambda, and both of them after this level increase their performance, their accuracy for the arithmetic task. As you see, scale and the size They are very important. Now let's look at these emergent abilities. We have three typical emergent abilities. Now I will elaborate these major abilities: in context learning, instruction following, and step-by-step reasoning. Of course, we have more abilities, but these are the core and very important abilities. And before starting, I must say each of them is a new topic. There are different methods and approaches to implement those abilities. For more details, you should check papers about each one. Okay, first of all, in context learning. Simply, LLMs can learn from a few examples and understand the context. So comparing to the supervised learning and labeling a lot of samples, this method is easy to implement. Also, you can just provide a few samples to the model in natural language. You don't have to add additional step to the development lifecycle. It is formally introduced by GPT-3, and this is quite critical. Model will not be trained again, no gradient update. That means it's also cheap. And of course, you can enhance the performance of the LLM with this in context learning. It is also helpful. And the second one is instruction following. Instruction following is also called as instruction tuning. In other words, you can think this is fine-tuning of LLMs. Fine-tuning is not new and it's not specific to LLMs, but instruction tuning is emergent ability of LLMs because you can provide instructions in multiple tasks and model can perform well in those tasks even though the model didn't see those tasks in its training data. So this is really powerful. And after implementing this, you will see significant difference in the performance of the model. And of course, here to see these emergent abilities, again, the model size is important. For example, for the Palm, 62 billion parameters are required. And the number three, step-by-step reasoning ability or chain of thoughts ability. You can see both of these terms. Actually, we can categorize this ability under the in the context learning because the idea is while providing the context and samples to the model, divide the task into subtasks or steps to teach the reasoning behind the main task. Let me give you an example of the article. As you see here, we have standard prompting and chain of thought prompting. Also remember, we have model here. Prompt is an input for the model. And the completion is the output of the model, right? So when you provide standard prompting like this one with a question and answer and question, so this is one-shot learning because you provided one example, one desired output for the question. And as you see here, for this example, the model output is just the answer. Here, as you see, for the same question, instead of just the answer, we have now the steps. Roger started with 5 balls, 2 cans of 3 tennis balls, each is 6 tennis balls. And then here, a sub-step, and then answer. Then, as you see, the model now generates the completion, which includes the steps. The cafeteria had 23 apples originally, 20 to make lunch, so they had 3, 6 more, then answer is 9. This is just a simple example to show the ability of LLMs, the chain of thought and the step-by-step reasoning ability. So again, we have 3 typical emergent abilities: in context learning, instruction following, and step-by-step reasoning. Of course, LLMs have more abilities and the field is dynamic. These are the core emergent abilities that were highlighted in the paper. Now let's look at some key techniques that are important to understand LLM. Number 1 is scaling. Larger model, data sizes, and more compute lead to improved model capacity. For more details, read the Chinchilla paper. I added the link to the description. And number 2, training. So large models, more data require parallel and distributed training. You can imagine the total cost, therefore we need to parallelize and reduce the cost. There are ongoing research on this field. And number three is ability eliciting. In the LLMs, some abilities are not explicit and direct. So you need to design suitable task instructions or specific in-context learning strategies to elicit those such abilities. To remember the step-by-step reasoning ability. You provided a good context learning. Now you have the ability of reasoning. And number four, alignment tuning. This is also very important. So training data of LLMs can contain potentially harmful, toxic, or biased data. And therefore, aligning the LLMs with human values is a necessary step. Okay. For more details, you can check the Instruct GPT and reinforcement learning by human feedback. And as you see here, the human in the training loop to align the model. And last but not least, number five, tools manipulation. So LLMs are trained with text data, so they can read and write. You can imagine like that. With additional tools, they can also speak and listen and watch. So we can use external plugins, and they can be eyes and ears of LLMs. To calculate advanced math, instead of using LLM, you can directly use external calculator. Then you can use a search engine and support the LLM. I think this will affect the industry and the products a lot. Okay, this is the end of the second part, and I tried to provide the big picture of LLMs and highlighted important features. Next video will be the closing video of the theoretical introduction of this video series, and I will show the last missing parts of the big picture, all LLMs and their map, and a brief explanation about transformer architectures, which are the core of the current state-of-art LLMs. Then we will start hands-on parts, and I will show OpenAI library and also some open source large language models. Thanks for watching. See you on the next video.